Okay, here's our status. We have this 2 over L squared times all this stuff, and we're just going to carry the 2 over L squared for the next step, so we're not going to worry too much about it, and let's look at what we've done in here. The L squared h to the 4th minus h to the 6th has a common factor of h squared, well, h to the 4th under the square root. We factor out an h to the 4th under the square root and then take the square root. We end up with h squared. We're left in here with L squared minus h squared under the radical. Over here, these first two terms have an h to the 4th in common. So we're going to factor h to the 4th out of these two terms, and we're going to get L squared minus h squared. These terms have a 96 in common, so we're going to factor out the 96. They also have L squared h in common. Factor out the biggest power we can. And we get 96 L squared h times L squared minus h squared. Now you can look at that. You can multiply that backwards if you like, but that's the way this factors. If we multiply this back out, we get this, which will help see how we got from here to here. Now we notice that we've got a square root of L squared minus h squared. We've got an L squared minus h squared that's common here. So we could factor out the square root of L squared minus h squared from this, leaving us just the h to the 4th plus the 96 L squared h. And that's what we're going to do in the next step. So let's back up a little bit and see how that works. Again, we see that every term, if we factor the square root of L squared minus h squared out of this radical, is going to contain a square root of L squared minus h squared. So that just becomes a factor of the entire polynomial, or the entire expression. It's not a polynomial, it's a bunch of square roots of polynomials. So we bring that square root of L squared minus h squared out in front, and now we've got a pretty simple term, pretty simple thing in here. Remember now, the L squareds and the L's are just numbers. The only variable here is h, and h only appears here, 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 and here. Now at this point we'll note that the 96 was the original altitude of the table above the floor, and we're going to replace that with y0, just to generalize as far as possible so that we could actually deal with any length of ramp raised to any height from any height of a table. And we get this final expression in red here. Okay, now it doesn't much matter which expression we look at. Remember, 2 over L squared is just a number. The square root of L squared minus h squared is a function of h. And then h squared plus the square root of h to the 4th plus y naught L squared h is a function of h. We do note that if the y naught was small or the L was small, then this would be like the square root of h to the 4th, which would be an h squared. So this is almost like h squared plus h squared for small values of y naught. We note also that we have two functions, essentially. The function in parentheses here, which is increasing, just kind of like an h squared function. Okay, so it's got a graph that's going to go up faster and faster. The square root of L squared minus h squared, on the other hand, is going to be decreasing, because of course by the time h gets as big as L, which corresponds to vertical ramp, we've raised the end as high as the length of the ramp, we're going to get 0 here. If h was equal to L, we'd get 0, which is exactly what we get for the distance, the x distance, if we drop the ball straight down. It doesn't go anywhere horizontally. So we have two conflicting things going on here. We have the square root of L squared minus h squared, which starts high and ends up low, ends up at 0, in fact, when h equals L. And we have the h squared plus the square root of h to the 4th y naught L squared h, which has a graph that's a lot like a parabola going up. We multiply these two together, so we have the influence of the parabola going up and the square root of L squared minus h squared going down, and at some point we start off with the parabola going up, but at some point this one takes over and everything starts going down again, as it has to, because remember, this is going to eventually equal 0 when h equals L. So we've got a product of two functions. If we can visualize the graph of this function and the graph of this function, we can visualize how the two graphs go together and allow the distance to maximize.